Hi everyone, welcome back to another seminar on reinforcement learning. So far what we've done is we looked at two types of methods. One is value-based methods, right? So here what we did was you map of a state action pair and then to exploit it, we take the highest action with the highest value. Right? And these kind of methods generally work better when you have a finite set of actions, right? Example of this would be Q-learning and deep Q-learning, right? And our update rule over here was basically, okay, the delta is going to be the learning rate and the reward function for that state and action plus max over all actions for state at t plus 1, right, minus our initial estimate for that state. Okay, into the gradient of, okay, so this is what we did for deep Q learning. So then we have policy based, what we did last week.
Paul,
yeah.
Can you explain each term of the equation more friendly?
Sure.
Yeah.
So basically, we are estimating the current value of taking a certain action at a particular state, right? So what we're doing here is we are doing a normal squared error, so it's called TD error, between this is your predicted value, right? Your current estimate of the value, and this is the actual value that you get. So currently the reward at this time plus the discounted future rewards.
Okay.
Right?
Okay.
And the gradient will depend only on your predicted value. Okay, so then we went to policy-based methods, what we did last week. So here what we do is, here we're going to map an action distribution for a state. Okay, so basically here we're learning a probability distribution at each state, deciding which actions to take. So it will learn to take better actions and will increase the probability of taking that action. Okay? And examples over here is policy gradient methods. And the update rule over here is so the derivative of your score function is going to be the expected value with respect to the log of your policy into the reward for that trajectory. Right? This is what we did last week. So
can you try explain this term in English? What is the J function, for example?
So this J theta is your score function, okay, and you're trying to maximize the expected future reward, right? So we did the derivation last week where we start off with just the scope function and we learned how to derive this term. Do you want me to go through that?
Can you give me a high-level explanation? What is the scope function?
So basically,
What is the input to the scope function and output?
the input is going to be your state,
Okay.
okay, and you are basically going to train a neural network by changing the parameters theta to maximize a scope function.
Yeah.
Right.
My question is,
Yeah.
what is scope function?
So your scope function is the expected reward for a whole trajectory.
Okay. So given state, expected reward for whole trajectory. Okay.
Right.
Mm-hmm.
Okay.
Mm-hmm.
But now what we're going to see is the issues with policy gradient methods. Okay. So the first issue is you have very high variance, and what I mean by that is, say for example you start at a state, say your start state. Okay.
Mm-hmm.
The first time you reach this particular state, you may take this trajectory.
Mm-hmm.
Second time you may take this trajectory. Third time you may take another trajectory, and so on. Okay? And another thing is, at each step, you could take other trajectories as well.
Yes.
Right?
Mm-hmm.
So you have very high variance and you have a lot of sources of variance. So at each state is basically a source of variance.
Mm-hmm.
Right?
So it means for each state there is not so many samples to get reliable expectation.
Right. So basically, if you have a huge number of samples, it will converge. But basically, what I'm trying to say is that convergence is slow.
Yeah, very slow.
Okay.
Mm-hmm.
So that is one. Now a second issue is, say for example, you start at this state, okay, and you take an action, and this is good. Right? You reach this state, then you take an action, it's bad. Right? It could be excellent. Right? And so on. Okay? This term over here is the reward for the entire trajectory. Okay? So you are, although ultimately over this trajectory you may have say a positive reward, you have many bad actions in between. Okay? So again, it's going to take longer to converge because you're averaging the bad actions with the good actions. Okay? And the third issue is, suppose you had a reward of +1 over here, and suppose +1 over here, say -1 over here, and so on. And suppose in this game you can die, right? So suppose suddenly you get a -20 somewhere over here. Okay? Your cumulative reward is going to be, suppose it becomes 0. Okay? Then this becomes 0, and then it doesn't learn. Okay?
Can you repeat the last part?
So this trajectory, so this is the reward over the whole trajectory. So it's basically a cumulative reward over the whole trajectory, right? So if that cumulative reward turns out to be 0, okay, there's no learning. Okay? So because of all these issues, convergence in the basic policy gradients is very slow. Okay? So now we're going to see how we can improve these methods. So basically the issues is high variance, the cumulative reward, when 0, and the third is bad actions, averaged with good actions.
So can you remind me why policy-based method is required? What is the advantage of it
Compared to Q-learning?
Yeah.
The main thing in Q-learning is that it works only with a finite set of actions.
Mm-hmm.
So say if you have in the continuous space, you cannot estimate the value for each point on your
Okay.
So
Yeah,
that's why
okay.
we use policy benefits. Okay, so
What is the basic difference between these two? In both the uses, let's say, score function, kind of score function.
right, but the difference over here is in value-based functions, you are going to estimate something like a table, okay, and you're going to estimate, say, for states versus actions. Okay, you're going to estimate a score for each action over the state, right? So for say state 1, you estimate action, this could be your future reward could be say 5, here it could be 0, here it could be -2, here 7, and so on, right? Whereas in policy based methods, what you're going to do is for each action in a state, you're going to learn a probability distribution. Okay, so say for state 1 again, the probability distribution is you're going to learn say 0.2% chance, means 20% chance to take action 1, say 0% chance to take this action, 3% chance, 30% chance to take that, and say 50% chance to take that. Okay.
So instead of absolute value, we are using the probability distribution.
Right. Okay. And this, so if you think about it here, suppose there are two actions that are very close to each other. Okay. So say this reward over here was 10. Okay. And this reward over here is 10.1. Okay. In this case, the probability distribution would be similar between the two rewards, between the two actions. Whereas in this, all you're going to do is you're going to take the one with the maximum value. Okay?
What happens here? I mean, if the distribution is the same here, what happens?
If it's exactly the same?
Like, close.
Here you're learning the distribution and then you're sampling from that distribution. So it takes care of your exploring as well as your exploitation.
Okay.
But if two paths have the exact same probability, you will equally sample actions from both of them.
Okay. So if there's 0.5 and 0.6 or something like that, I would choose the path with 0.6 and explore that path.
Not necessarily. At every time when you reach a state, you have the probability distribution and you sample from there. So you could even pick a sample from this one.
Okay.
Or this one.
So if one action has more probability, it will be choose more of often.
Yeah, that's right.
Okay.
Okay, so now we're going to look at ways on how we reduce the variance. So the first thing is, what do you mean when you have this scope, this reward for an entire trajectory, right? This is the summation from time 0 to t minus 1, the discounted reward at that time t, right? Okay. But what this means is, this is the reward.
Is the discount constant or is it like
It's a hyperparameter. It's normally between.
is there any exponential term?
Oh yeah, sorry. You're right. This should be t. Okay.
Mm-hmm.
So one way to think about this is, and what we used last time in the code, we used the discounted future reward, right? So we're going to change this slightly. Okay. Let's say it's k is equal to t until t minus 1. K for the reward at time t. Reward at t. Right? So what this means now is, you can think of it as reducing the number of variables that is affecting the variance, right? So at this point, say your first point, so this is your start and your end, okay? It will be the reward from the entire trajectory. At this point, it's going to be the reward only from here to here, right? This point is going to be from here to here. So it's reducing a few variables, right? So that's the first method. So this is discounted future reward. Okay. Now we come to what's called actor-critic methods. Actor-critic methods, basically what it does is instead of using this, what if we could estimate this value? Okay, and so basically what they do is they club policy gradients with value-based methods. Okay, so it's going to use a second network to estimate this value. Okay,
It's the future expected.
right. So because this is technically the future discounted reward, but now they're going to use a network to do it, and then so given a state, okay, at least this is my intuition of it, given a state, when you're using a network, okay, without any learning, every time you come to that state, you're going to get the same value, right? And that's my intuition on how it reduces variance.
Can you explain again? I didn't.
So this is my intuition. It's basically when you use GT, okay, so say you come to some state, you could take this path, this path, this path, and so on. You could have different values, right? But when you're using a network, this is always going to give you one value at this state.
Mm-hmm.
And that's why it reduces variance.
Okay.
Right?
Mm-hmm.
So that is one reason why you use actor-critic, and the second reason is you could, but it's not used that often, is basically you could now convert this from a Monte Carlo, into a temporal difference method.
Can you explain the idea behind the Monte Carlo
Yeah.
and the
So-
temporal difference?
In Monte Carlo, you basically need to wait till the end of your episode, right? You wait till the end and then you calculate your future discounted rewards backwards, okay? And then you update at the end of your episode. Whereas temporal difference, from here to here, if you have an estimate of the Q value here, you can update at this point itself,
Mm-hmm.
okay?
Okay.
And that's what temporal difference is.
Can you explain? I forgot. I'm sorry. Continue.
That's okay.
Yeah. Why the name actor critic?
Yeah, so in actor-critic, your gradient update is now going to become right? So this is parameterized by theta and this is parameterized by another set of weights, okay? Because we have two networks here.
Mm-hmm.
This part is the actor that is learning the probability distribution and is deciding what actions to take.
Mm-hmm.
And this part is a critic, which is basically telling you how good the action that you took
Mhm.
is.
Okay.
Okay.
Paul, can you explain the relationship between R trajectory, R tau,
Mhm.
right? R tau and the Q function.
So the Q function is this,
That is the Q function.
right? The Q function is basically your
Okay.
expected future discounted rewards.
Okay. So
But this is the actual value that you get in a trajectory, whereas this Q is an estimate.
mm-hmm. That Q is an estimate. So and you are basically in the formula you just replace
Right.
R tau with
With-
the Q function,
Correct. Yeah.
but the definition is slightly different.
Are you talking about this?
Yeah.
So basically, in this co-function, okay, you are replacing this with, first we replace it with GT, right?
So how we can replace? Is it same?
So basically, when you think about it, and that's what I was explaining, right? The whole trajectory starts from here to here, right? So you're trying to maximize the rewards over a whole trajectory. Okay?
So expected reward.
Yeah.
So if I, can you check if I'm understanding
Yeah. No,
correctly?
I got your question.
Expectation of the R tau is the same with the expectation of the GT.
Okay, let me just finish this and then we'll decide that. So at this step, okay, you cannot do anything to change the reward from a previous step. Okay, and that's why we can discard it.
Okay.
Okay, at this step you cannot do anything about this because it's in the past. And in a Monty, in a Markov decision process, you can it depends only on this and the next step. If I'm not, yeah, it depends only on the current step, right? The past does not play a role in your future.
That's the Monte Carlo.
Markov decision.
Okay, so
Okay, so we first replaced it with GT, just the future rewards, and now we're replacing it with the estimate of the future rewards.
so can you use mathematics? So expectation of that part. I would like to see
Yeah.
how there should be some mathematics here. And using the expectation here. Do you think you can do that? I
Yeah.
think.
Just one more thing is
Oh no, GT, yeah. GT or QT? Is it a GT or QT?
this is G.
Yeah, GT,
And then,
yeah.
Q
yeah.
is when it's. One more thing I left out here is this is the sum over from t is equal to 0 to t minus 1 for the whole trajectory. Okay.
Maybe because it's expectation, if you add a summation, you will probably have to multiply by probability. Am I right? Or not?
No, so you can do it. It's just that we could start from scratch again. So. I'm gonna replace this with GT over here, but here we can use the log derivative trick. So okay, and then now this is a different expectation. This is the probability, and we reformulate it. This is your x, so it becomes the expectation of right. So instead of maximizing the reward of the whole trajectory, we're maximizing just the future reward here, but you'll end up with the same equation.
I'm sorry for I'm learning here. Why we are getting expectation of the GT?
So this is GT. I just replaced it. I can put it back into this. Should I write that?
No. The first term.
So I've started again, right? Initially, how we derived this was we started off trying to maximize the expected reward over the whole trajectory, right? This is what we started with. I wrote that here. This was our score function, right? So instead of using this, we just changed the score function to be the expected value of GT, which is the summation of the future rewards. Right? So I'm starting now with this.
So I am maybe a little stubborn,
Sure.
right? The R tau and GT is not same.
It's not same. No.
So J theta is J pi. Is it J theta or J pi?
This theta.
J theta was previously expectation over R tau,
Right.
but how we change J theta with the expectation of it's the same GT. Yeah.
Expectation of R tau is changed to expectation of GT.
Yeah. Why?
Okay,
How we can do that?
Think of it this way, right? I am defining my score function here. I can define it as anything that I want,
So you can define anything you want.
right?
So instead of
But so both of these will converge,
Mm-hmm.
right? It's just that you are reducing the variance that way to make it converge faster.
So what you are saying is there is no definition of the score function J.
No.
no, instead of the entire trajectory, it's going to use that instead of using the reward over the entire trajectory, he's just redefining the thing as just having the discounted future reward. Instead of, because that takes out the case where you are accumulating over the positive and negative.
So my question is here. My question, so Sanas, my question is, can you move?
Yes.
Yes or not?
No.
No.
No?
No.
Okay,
It's
a no.
equivalent.
But previously it was this. But now we redefine J theta.
Correct.
Yes.
Okay, so okay then let's continue.
Okay, where were we? So we reached actor critic.
So there should be a sigma somewhere in the new definition.
Sigma.
There was a sigma in the here. So summation here. There should be something here.
Correct. That's a summation. Okay. So this was, we've replaced it with an estimate.
I just
And
one question.
yeah,
So there you wrote R equals 0 to T-1 or T to T-1?
T.
T,
Yeah.
yeah. It is.
Okay. And this is also called Q actor critic. Okay, because it's using a Q value. Then there's something called advantage actor critic. Okay. Now, what an advantage is, it's basically, it tells you how much better taking a particular action is versus the average value from all the actions in the state. Okay. So what we basically do here is, instead of using the Q value, okay, you have advantage, SNA.
So
Sorry.
I'm
Yeah.
sorry. I'm so sorry.
No problem.
Yeah. So this is T, right?
Yeah.
So here is my question. Let's say hold on. Is it this correct or
No,
no?
no. Because this part, right,
Mm-hmm.
is still over all your time steps.
So my question is there parenthesis, is it this summation over here or so?
Okay, let me write it completely.
Mhm.
Remove this. Okay.
Mm-hmm.
Okay. Sorry, this was here, right? The trajectory. Let's write it over here. Okay. This is a summation. of t minus 1 okay.
Okay. According to the definition, it should be 0.
No, so that's what this was the reward over the whole trajectory,
Mm-hmm.
and this is the GT, which is the only the future rewards.
Yeah. So I might be wrong, and I'll stop here. But Paul, would you please check the textbook again
Sure.
to see if there is if those J function used in the policy-based policy gradient method and the activity is actually same. J function is actually J score value is the same,
Yeah.
might be same. That is my question.
No, it will not. But I
It
can
will not-
double
yeah,
check.
yeah. Please check. Yeah.
Okay. So then we have what's called an advantage. So an advantage is basically you can think of it as okay. What this means is the Q value is the estimate for taking one particular action, right? And your V value is the average value for all the actions in a state, right? So suppose your average value is going to give you a reward of 10, okay?
Then it should be V of S, not V of AS.
Yeah, sorry, V of S.
Mm-hmm.
So suppose it's going to give a reward of 10, and say you take an action, say going left, okay? It gives you 15, okay? So that means your advantage is 5 over the rest of your states, okay? And if it's a bad thing, say this was just 5, then it becomes minus 5, okay? So an advantage tells you how good or how bad this action is compared to all the other actions in the state, right? So then what they did was they replaced the Q value with the advantage, okay? And in order to do that, you may think that you will need 2 more neural networks, one for this W and V. But what they did was they efficiently did it with just one network. So what they did here is they take the reward at that time, t plus 1, plus the value for current state t minus is that right? Sorry, this plus 1 minus the current state. Okay? So you can now do this with one network. So this was advantage active critic. So then your score function becomes, the derivative of the score function becomes and the reason why we do this is again to reduce variance. And I'll take a very simple example, and you can double check this on say Wolfram Alpha. Is suppose this value, suppose we just take 3 dummy hypothetical values, so 0.5, 0.2 and 0.3, okay? And suppose your reward function was something like 1000, 1001 and 1002, right? So if you calculate the variance of this, it's going to be 0.5 into 1000, comma 0.2 into 1001, comma 0.3 into 1002. Okay, so if you check the value of this on Wolfram alpha, you will get something like 2000. 23,286.6.8. Okay. Whereas if you subtract a baseline, say the mean of this, which is 1001, so then you're checking the variance between 0.5 into -1, 0.2 into 0, and 0.3 into +1. Okay. In this case, your variance is going to be 0.16333. Okay, and that's why they introduced a baseline.
Is
Yeah.
it 0 to t there again? In advantage?
Yeah.
Or t to.
This is always from all your states, from your initial state to your end state. Okay. Only this part becomes so the reward part is on your future discounted rewards, but you still want to maximize the expected value over all your states. Okay. Any questions on this?
Is it VB or T plus 1 plus?
Where is that? Yeah.
Yeah.
V, this is subscript V for your weights. Okay. Can I erase it? However, there are still issues with active critic methods, and the main issues is one is these methods are very sensitive to hyperparameter changes. Okay, so there are many factors. So basically, reinforcement algorithms are very brittle. It's possible that suddenly you'll get an update which is very large, that causes a very large step, and it's unable to recover from that step. Okay, so basically, there will be very large updates. And another thing is that these methods, especially policy gradient methods, are on policy methods. That means whenever you're training it, you sample from your data, your environment. Okay, you train it using that sample, and then you cannot use that sample anymore. It's one time because it's on policy. It has to sample from the current policy. Okay.
Can you explain on policy again?
So what it means is we are learning this policy, right? When you're sampling from it, you sample records, then you make an update to this policy, then those sample records cannot be used to train anymore. Okay, you always have to sample from the current policy.
Okay.
Okay, and so then they came up with what's called TRPO, which is Trust Region Policy Optimization. Now that is a method that the intuition behind it is basically to restrict these large updates. Okay, but it's very complicated, and it basically uses KL divergence so it basically compares the old policy with the new policy, checks how much difference there is, and then they adds a constraint to limit that update. If it's too large, it reverts it. I think it reverts it. Right? But again, it's not efficient, and it's still on policy. Okay, so PPO was created by the same authors of TRPO, and they made it. Their goals were basically to make it simple to understand and implement. It should be sample efficient, and it should not be sensitive to these large updates and hyperparameter changes. Okay, so that was the goal with which PPO was written. So in order to get into PPO, I first need to go into something called importance sampling. Okay, so importance sampling is basically when you have an expectation, right? You can write this as right? Now, importance sampling basically what it does is you can use another distribution, okay, to estimate this distribution. Okay, so what they do here is you divide and multiply this by another distribution, say Q of x. Okay. Now this is another density, probability density function. So this becomes the expectation of x with Q. Okay. Okay. So in PPO, what they're doing is to make it sample efficient. They are able to. They basically have two policies. One is the old and the new. They are able to sample from the old to estimate the new. Okay, that makes an update for k epochs, and then it copies the new parameters. The parameters from the new policy to the old policy, and then redoes it.
How does that lead to importance sampling?
So I wouldn't be able to explain this very well because it's a lot of mathematics, but basically when they do this, right, this expectation is equal to this expectation, right? So using this and sampling from QX, okay, they are able to estimate this with respect to P. Okay. So in terms of PPO, basically what they did was, instead of using this, okay, so let's just write the score function. This is firstly the gradient of the score function. So the actual score function, let's say this is the score or loss, whatever you want to call it, for policy gradients, okay, is equal to the expectation of you can put the reward here, or you can put GT, or let's say the advantage over here, okay, at time. Okay, so this is not the gradient, this is the actual loss. Okay, so you can replace, what they did was they replaced this with, so this is going to be the loss for here, this is theta old. Okay, I'll show you how this equals this in a bit, but the intuition behind this is basically you're going to get a ratio over here between the new probability distribution and the old one. Okay, so if this is r theta, okay, if this is 1, that means this and this is equal for that state, right? If this is greater than 1, that means taking that action is now more probable, right? You've increased the probability of taking a specific action. But if this is less, that means you've reduced the probability of taking this action, okay? And what they want to do over here is they define this ratio and then they want to clip it so that there's not too much of a change between the old and the new distribution. Okay, so how they did that was they used a clip function, and the beauty of this is they were able to add this clip in the objective function itself. So so the minimum of this, or the clipped value between okay, and how this clip works is this is when your advantage is greater than 0. And let me give you a simple example of this as well. So suppose your ratio is 2, okay, and your advantage is 1, okay. This will, and let's just do it for 1 times now, right? So this is going to become the minimum of 2 into 1, and the clipped value of 2. In the paper, epsilon is 0.2. Okay, they tried for different values. They have 0.2, and then there's another paper later for an adaptive epsilon. So let's just take 0.2. So this is going to be 1 minus e, so 0.8 to 1.2 into 1. Okay, so this is now going to be minimum of 2 comma, this is going to get clipped, so it's going to become 1.2, right? So minimum of that is going to be 1.2. Okay, whereas if you take another example of say a negative, so your ratio is, say it's 0.6 and your advantage is now -1 because it's less probable, right? So then if you have a min, this is now going to be 0.6 into -1, comma clip of 0.6, 0.8 and 1.2 into minus 1, right? So this becomes minus 0.6 comma this minus gets multiplied by this will get clipped to 0.8, so minus 0.8, right? So this min of these two is going to be minus 0.8.
Or what does that clip do?
A clip value is, say, this is the input to the clip, this is the minimum value that it can take and maximum value that it can take. So if this value is in between these two, it will take the same value, but if it's beyond this or less than that, it will take the limit of those two. Okay? Any questions?
What did you say the min does? Can you just explain?
So this basically the idea was that they should restrict the updates. They don't want it to be too large and they don't want it to be they don't want to increase their probability of taking action by too much and they don't want to decrease it by too much as well. So they came up with this clip objective function that when I say r theta is 2, that means taking that action is now twice as likely.
Okay.
Right? But they want to restrict that. So if it goes through this clipped function, this gets clipped at 1.2 and then they'll take the minimum of these two, right? So in this case the minimum will be 1.2, but say it was not 2, say it was say 1.1, right? So in that case you will have minimum of 1.1 comma clip of 1.1 comma 0.8 comma 1.2, right? In this case this doesn't get clipped because it's between these values, so it will remain a minimum of 1.1 comma 1.1, which is equal to 1.1, right? So it will clip the value only if it's too large or too less.
Okay.
Okay. Can I erase this? Oh, erase that. We don't need this anymore. Okay, so let's just denote the expectation at a particular time step. So I'm not keeping the summation inside, right? So this was into your advantage at time step, right? So this is equal to the integral right? Okay, so this cancels out. You're left with the integral of okay, and this was your scope function, your new scope function. And now let's take the derivative of that. I'm taking the derivative inside. Okay, and again we use the log derivative trick, which is derivative of log x equal to 1 upon x into derivative of x. So therefore derivative of x is equal to x derivative of log x. Right? So this becomes phi theta derivative of log. And this is we reformulated to use this as the probability distribution, which becomes the expected value of
What's the last step?
the last step is we basically show that the derivative of this is the same as the derivative of using a normal policy rate.
Okay. Just to make sure that they both are doing
Yeah.
the same thing.
Any
And
questions?
that's the part where you said they're multiplying it with another distribution in order to find the distribution of this, right? When you're introducing PPO.
Correct. I showed you both multiply and divide by the other distribution, and then you reformulate that expectation using the second distribution, the expectation.
So the final derivative of j is
Yeah.
what we started, right?
Yeah. The only thing here is the advantage, but if you start using the advantage over there, it will be the same thing.
So that is the more the vector critique,
Right.
and actually you go into the PPO where you clip the
Right.
values.
Yeah.
Okay.
And basically, so PPO, there were 3 upgrades over Active Critic. The first one was the main thing was the clipped what's called a surrogate policy function, policy objective. The second one is it's off policy, right? To increase sample efficiency. And the third thing that they do is they use mini batches. So they sample from the old policy and then conduct k epochs using mini batches to update the new policy, and then they copy the values from the new policy to the old policy, and then they repeat the process.
So we can do the mini batch because of it is off policy.
Right.
And can you explain what is on policy and off policy in a concrete example?
Okay, let me diverge a little bit and talk about Q learning and how that is off policy. Right. So in Q learning, what generally happens is, and if you we also, I think we implemented a memory, right, where okay, let me just write the formula for Q learning again. Can I erase this?
Yeah.
What is after 1 minus epsilon?
1 plus it.
1 plus epsilon and then the advantage into the advantage over here. Okay, so in Q learning, what we did was we were doing TD error between this and this, right? So what we did was we created a memory, okay? And say we had about 2000 samples in the memory. At each point, we were sampling 32, right? 32 records, and we were optimizing the Q value, right? Now, in our network, so we had the states, we were storing the states over here, okay? So we had 2000 samples, we had the states, and we had the actions that we took, right? So, using our network, all we needed was the state, right? The state and actions to pass into a Q network, right? So, we could optimize this using the old samples, right? Because here, what do we need? We needed the max of this. This could be got from our Q network. We needed this, which could be got from our Q network. And we stored the rewards as well at that time, taking an action A, right? So we got this as well, right? So we could keep estimating the Q values using the old examples, right? So it's off policy. And
old example meaning, what do you mean by old example?
so we are storing the states, action and rewards in a memory, right? So when we are going to optimize this, we are not sampling. We've already sampled those records, right? Then we go to optimize this, okay? And then obviously we'll keep refreshing the memory every little while, but we'll refresh maybe say 100 examples or something, right? And we'll throw out the oldest 100 examples, and then we'll keep sampling 32 records at a time. Okay.
It's too difficult for me. Can you
Okay.
give
So
me a simpler?
basically, off policy means.
So let's say if we do a Q running, it's off policy. If we do a policy gradient, it's on policy.
Right. And why it is because on policy means in order to optimize it, you need to be sampling from the current policy. Okay. As soon as that policy changes, you cannot use those records anymore.
Yes. Now I think I can get the idea a little better.
Yeah.
But it would be great if an example of when policy changes, optimization changes in a multi-amp bandit using multi-amp bandit is the most simple one.
Okay, so let's say normal policy gradient, we had our loss was the loss for policy gradients was the expected, I'm saying for time step t is the derivative of log at given st into set gt, right? So say I take the first sample, okay, and I sample it from the environment using that policy, okay, and now I got to optimize it, right? I can optimize it so this this value changes. Okay, so say at this point there were 3 actions, left, right, and do nothing, right? So suppose this was 0.3, this was 0.2, and do nothing was 0.5. Okay, so I'm able to optimize this. Okay, now suppose I try to rerun using the same example after this has already changed. Suppose this changed to maybe left was 0.4, right was now 0.1, and do nothing was still 0.5, right?
Okay, makes sense.
Right?
Yeah,
Yeah,
I think I got the idea. And I have one more question, Paul. What is the model-based reinforcement learning and model-less?
Yeah, so model free basically
yeah.
means you do not need to model the dynamics of the environment. Okay, so in
all of this method is model
all
free.
model free.
Okay,
right?
I see.
Yeah.
Okay, I think our time is up.
Yeah.
You guys can keep asking him if you guys have a question.
Sure.
Is there any more questions?
Finally, explain how PPO works. The PPO algorithm.
Yeah.
And
Do you have any questions on it?
no. So it's basically improvement over policy gradient.
It's an improvement over advantage actor critic.
Okay.
And advantage actor critic is an improvement over policy critic. So it's like a higher step.
So this is called A3C.
No, so advantage actor critic is A2C, which basically A3C actually came out first, and what they did was they had many parallel environments running. Okay, and it's called asynchronous advantage actor critic. So that's why it's A3C. And what they were doing is they had many parallel environments running, and each was I don't know exact architecture, but each was sampling separately, updating, and then basically updating it to one common network. Okay, and then this common network's weights were getting updated back into these every few epochs. Okay, but then this had a lot of extra computational overhead and stuff, and then they mathematically proved that this asynchronous behavior doesn't really help. So there was no basis of using that asynchronous behavior, and that's why then they did A2C, which is just advantage actor critic. And what they did was they still had parallel environments, but when updating the main network, they would wait till all these completed first, then updated they updated this at one time, and then they copied it to these parallel environments. Whereas if I'm not wrong, A3C at certain points of time these were out of sync with the main network, and then there was some overhead.
Okay, in Udemy course, what level is the PPO? There are 3 lectures.
That's
3
in the
seasons.
second one, I think.
But
I didn't get through the full course.
Okay.
I actually started from the first one, but I didn't like that course so much. And then I found a very nice link, especially on these algorithms. And I've posted that in the journal, if you all want to.
Where did you post it?
In the lab seminars. So we have the resource links. So I've posted it.
Okay, thank you. Alright guys, next week